this lecture, we're going to study combinatorial classes that are associated to regular languages. So to this end, let's take A to be alphabet, a finite alphabet with, let's say, k elements. Then we've already seen the combinatorial class W of words in A. So this is actually the set A1, A2, AN, where n is some non-negative integer and A1, A2, etc. These are elements of the alphabet. And we've seen that this class has generating function 1 over 1 minus nx. They're precisely, not nx, kx. They're precisely k to the n words of length n. That's really easy. Okay, and what we'll be interested in are generating functions for formal languages. So what's a formal language? A formal language, and here formal is used as opposed to natural languages like English or Sanskrit or Tamil or whatever, is a subset. So a formal language, maybe you need to specify the alphabet. A is any subset L of W. So for example, the set of all computer programs that can be compiled by a C compiler this is a language in the ASCII alphabet. And but these kinds of examples are extremely complex, and we will not try to subject them to combinatorial analysis. Let me give you another example. Let's take A to be just a set with two elements H and T, which you can think of as coin tosses resulting in heads and tails. And ties is the language set of all words such that number of heads is equal to number of occurrences of tails. So maybe I'll just write it like this, W in W such that. So these are all words, there will be a bunch of heads and a bunch of tails. You're just saying that the number of occurrences of heads should be equal to the number of occurrences of tails. And now if we want to think of these as combinatorial classes, just inherit the size function from W. So the size of W is equal to the length of W for every W belonging to N. So for example, if you look at this language ties, then the number of ties of length, so there you can only have a word with equal number of heads and tails if the word is of even length. So if length 2n is 2n choose n, because you have to decide where the heads go and where the tails go out of the 2n letters, n of them will be heads. So you just choose those n positions where the heads go and put tails in the remaining positions. So what we get is ties of x is equal to 1 plus 2x squared plus 4 choose 2 x to the power 4 plus 6 choose 3 x to the power 6 and so on. Or I can write that more compactly as summation k goes from 0 to infinity. Well, let's just write n goes from 0 to infinity to n, choose n, x to the power 2n. There are many different ways of describing languages, and one of the particularly simple and nice ways of doing so is by using what is known as a regular expression. So what is a regular expression? So a regular expression, I'll define it by sort of saying what kinds of constructions are allowed with regular expressions. So a regular expression is the smallest class of expressions such that, so maybe we'll give this class a name, some smallest class, and let's call it R. So firstly we postulate that epsilon, this denotes the empty word of length 0, belongs to R. Then secondly we postulate that A belongs to R. This is the word with just one letter A. So every one letter word belongs to R. And then thirdly, if U belongs to R and V belongs to R, then we'll write a symbol with a vertical dash which will denote U or V belongs to R. So if U is a regular expression and V is a regular expression, then you can write down this formal symbol U dash V, and that's again a regular expression. 4, if U belongs to R and V belongs to R, then U dot V belongs to R. This is supposed to represent concatenation of words. This is supposed to represent the OR operator. And finally, if U belongs to R, then U star, this is called the clean star, named after the mathematician Kleene who introduced this. And what this is supposed to mean is the sequences of words, that is, you just take a word which is in R and repeat it many times. So I'll come to that more formally in a moment. So what does it mean for a word to match a regular expression? Let U be a regular expression and W be a word. Then we say W matches epsilon, the regular expression epsilon, if W equals epsilon, the empty word. W matches the regular expression corresponding to a letter A if W is the single letter word A. We say that W matches U or V if W matches U or W matches V. So this is a recursive definition of matching. You'll be able to reduce this checking by breaking down your regular expression into its atomic constituents using these operations. W matches U dot V if W is of the form W1, W2, where W1 matches U and W2 matches V. And finally, we say that W matches U star if W is of the form W1, W2, Wn for some n greater than or equal to 0. This includes n equals 0, so W matches U star if W is the empty word and Wi matches U for each I going from 1 to n. Okay. So this kind of matching is has a very popular implementation. Most computer implementations are not as bare bones as the one I have described here, but for mathematical purposes, this is this simple sort of regular expression description is the easiest to work with. But the implementation that is essentially equivalent to this but provides you a few more facilities would be familiar to those of you who use Linux. There's the grep utility. So it was built for Unix, and it's really global search for regular expressions and print. It's a popular implementation of regular expressions in Linux, and we often use this to search for text in files. It's quite fast and powerful. So let me just give you some examples of what these regular expressions do and how matching works. This description here may be a bit formal and also maybe a bit terse. So let's look at it for example. So here's a very simple example, the sort that you may have used if you use grep. So here's a regular expression, C-O-L-O-U. No, so we have two spellings for the word color. There's the American spelling, which is C-O-L-O-R, and C-O-L-O-U-R, which is the British spelling. And we want to search for either of these variants. So a regular expression that would do this job is this. So we don't write the dots in regular expressions, but this matches two words and color, because we say that either we have nothing here or we have a U at this stage, and the other letters are C-O-L-O and then possibly U or not, followed by an R. Let's look at a slightly more interesting example. What if I want to look for binary expansions of integers, of non-negative integers that are even? So here I'll write down a regular expression for binary expansions of non-negative even integers. So what we know is that such a regular expression, such a binary expansion must end with a 0. And before that, it can have zeros or ones. So you can have a string of zeros and ones, and then it must end with a 0. However, it cannot start with a 0. So we'll put a 0, a 1 in front. So it starts with a 1, then it has a bunch of zeros or ones, and then it ends with 0. And then in the end, but this will not match the binary expansion of 0, which is simply a 0. So we also say this thing or 0. And this is a regular expression that matches the binary expansions of non-negative even integers. Okay, we are now ready to define an S-regular language. So a language L is said to be S regular if it consists of all the words that match a regular expression, a given regular expression. So if U is your regular expression, then we'll say LU to be the set of words that match U. And this S regular means specification regular. This language is specified by a regular expression. Now we are interested in counting the number of words of a given length that match a given regular expression. But this becomes complicated sometimes because, so let's look at an example. It could happen that a word matches a regular expression in more than one way. Let's take the regular expression U to be A or A star. And now if you look at the word A, this matches this regular expression in two ways. Firstly, it matches A, and secondly, it also matches A star. So it has a non-unique way of matching this regular expression. So let's just make a slight restriction on the kind of language we are looking at. So suppose we have an S regular language, we will require that every word in that language matches the regular expression uniquely. So what does it mean to match a regular expression uniquely? To explain this, it's best that I just go back to what it means to match a regular expression. So we say that W matches epsilon if W is epsilon. Of course, this is going to be unique. So we'll say that W matches epsilon, and let's use a different color here, uniquely. There's no ambiguity here. W matches A, again we'll say uniquely if W is equal to A. Now in the third kind of matching rule, there can be an ambiguity. It could be that W matches U and W matches V. Or it could be that W matches U in more than one way, or W matches V in more than one way. So we'll say that W matches V, U or V uniquely if W matches U uniquely or W matches V uniquely, and then we'll add the stipulation, but not both of them. So you cannot have that W matches U and W matches V. That will become a non-unique way for W to match U or V. And now we say that W matches U dot V uniquely if W has a unique decomposition. So this can be written uniquely in a unique manner where W1 matches U uniquely and W2 matches V uniquely. And finally, we'll say that W matches U star uniquely if W has a unique decomposition. It can be uniquely written as W1, W2, Wn, where Wi matches U uniquely for each I. Okay, so we have this notion of matching uniquely. And then it becomes suddenly easier to write down generating functions for for the language. So let's just look at this. So assume, suppose every word in LU matches U uniquely. Then it is easy to write down the generating function for LU. Let's call that just ordinary LUX for LU. And how do you do that? So remember, what is this LUX? It's the sum over all W belonging to LU, X to the power length of W. And we have L of epsilon of X. Well, this is just equal to 1. Then we have L of A of X is equal to X for every A in A, doesn't depend on A. We have L of U or Vx equal to LUX plus LVX, provided that every word in L matches U or V uniquely. And then we have L of U dot Vx is just LUX times LVX, provided again that every word in L U dot V matches U dot V uniquely. And then finally we have LU star X is equal to 1 over 1 minus LUX, again provided that unique matching. So because if you have non-unique matchings, then these will be overcounts. There will be certain words that get counted in both these expressions here, for example, or words that will get counted more than once in these expressions on the right hand side. So we need that these matchings happen uniquely. So let's see how this is very so here's one immediate conclusion from this. If words in LR LU match U uniquely, then of course LUX is going to be built up from 1 and X by using the operations of plus, multiplication, and 1 over 1 minus whatever. So this will always be a rational function. Let's look at some examples. So here's a problem. Find a regular expression. R such that, let's say U such that LUX is equal to 1 over 1 minus X squared. So let's see, can we write this in terms of these steps? So yeah, so what we'll have is that U is equal to V star, where LV star of X is equal to X, LV of X is equal to X plus X squared. So if we can just think of a language where whose generating function is X plus X squared. So this is going to be a finite language. It's going to have one word of length 1 and one word of length 2. So this you can easily cook up something like this. Let's take A to be the alphabet with just 2 letters. Let's say A and B, and let's take V to be the regular expression. Either you have one letter A or you have 2 letters B. I couldn't write A or AA because then this would not be, well, that would still be, I guess, uniquely parsed. But I'll just take this A or BB. And then I couldn't take A or AA because if I took U equals V star, then it would not be uniquely parsed. And so what we have is U equals A or BB whole star. Words in this will be words in A and B such that the B's always occur in even number of times consecutively. And then you can see that this will of course have this generating function, just because a or bb has generating function x plus x squared, and this is v star, so it will have generating function 1 over 1 minus lvx. Okay, let's look at so what's the number of words in LU of length n, let's say fn. Then what we have is fn. So if you have a word of length n, either it ends with a, in which case it is obtained from a word of length n minus 1 by putting an a at its end, or it ends with bb, in which case it's obtained from a word of length n minus 2 by putting bb at its end. This certainly holds if n is greater than or equal to 2. And the base case is f0 equals 1, the empty word f1 equals 1. So what you see is that fn is the sequence of Fibonacci numbers. This is the nth Fibonacci number. And you could call this the Fibonacci language, or the Fibonacci regular expression, which is matched by words in the Fibonacci language. What I want to say is that LU is called the Fibonacci language. Now let's look at one more example. Suppose I know that my generating function is Lx. Suppose I have a language with generating function Lx equals n greater than or equal to 0 to n, choose n, x to the n. Why call it Lx? We already have a name for this. This is called ties of x. So if you think about it, this is nothing but 1 over 1 minus 4x to the power half, right? Because if you look at this right hand side of this equation, it is 1 minus half into minus 4x plus minus half into minus 3 by 2 into 1 over 2 factorial times minus 4x squared plus minus half into minus 3 by 2 into minus 5 by 2. Then we have 1 over 3 factorial minus 4x cubed and so on, which you can think of as sum n goes from 0 to infinity. What's happening here, I have a product of odd numbers in the numerator up to 2n minus 1. And then I'm dividing by 2 to the power n, n factorial, and then I have 4 to the power n, x to the power n. But this is nothing but sum n goes from 0 to infinity, and now I can I can put in 2, 4, 6, 8, that will be 2 to the power n times n factorial. So what I'll get is 2n factorial divided by n factorial x to the power n, which is summation 2n choose n. This should be x to the power 2n here. So here I guess I want x squared. Yeah. I only want even powers of x. And so that's so ties is this is not a rational function. So you can conclude that ties x is not a regular, well, ties is not an S regular language. Well, there's a slight issue with what I've said, because this just shows that TIES is not a language that matches a regular expression where every word matches a regular expression uniquely. But the point is here to note is that if L is an S regular language, then there exists a regular expression U such that each word in L matches U uniquely, and L is equal to LU. So I can replace the regular expression by another one where the matching is unique. I'm not going to prove this. This is a theorem. I'll leave it at that. In the examples that we'll see, it will be clear that the regular expressions are matched uniquely. So let's look at a very nice application of this idea and try to get a generating function for counting set partitions with exactly k parts. So for this, I'll introduce the notion of the restricted growth word of a set partition. So suppose X is a partition of the set 1 to n, so X is an element of pi n, and X has standard form B1, B2, Bk. These are the blocks of X. And as always, we assume that the elements of each block are written in increasing order, and the blocks are arranged in such a way that their least elements appear in increasing order. Then the restricted growth word of X is the word W equals W1, Wn. It's going to be a word of length n, where Wi equal to j if I appears in the jth block. Let's look at an example. Suppose we take X to be the set partition 1, 3, 6, 2, 5, 4, 8, 7. So this is a set partition in pi 8, and let's write down its restricted growth word. So W1 will be the block in which 1 appears. So W1 will be 1. W2 will be the block in which 2 appears. So W2 will be 2. W3 will be the block in which 3 appears. So again, it's going to be 1. W4 is the block in which 4 appears. It's going to be, well, the third block. 5 appears in the second block. 6 appears in the first block. 7 appears in the fourth block. And 8 appears in the third block. So this is the restricted growth word of this set partition. And X can be recovered from W by the rule that J lies in the Wjth box. So what I'll do is, given this 1, 2, 1, 3, 2, 1, 4, 3, I see that the largest term here is 4, so there must be 4 boxes. So I'll just draw 4 boxes, box 1, box 2, box 3, box 4, and I'll start filling these boxes with the elements. So what I'll do firstly is, I'll remember that these are in places 1, 2, 3, 4, 5, 6, 7, 8. So they correspond to the elements 1 to 8. And then I'll start putting these inside the boxes. So 1 goes into the first box, because this green one appears under the letter 1. So that says 1 goes in the first box. 2 goes into the second box. 3 goes into the first box. 4 goes into the third box. 5 goes into the second box. 6 goes into the first box. 7 goes into the fourth box. And 8 goes into the third box. And you see, this is exactly the set partition that we had started out with: 1 3 6 2 5 4 8 7. So you can recover a set partition from its restricted growth word. So if we want to count set partitions, we just have to figure out what are the possible restricted growth words. We can think of this as a language. So I'll say RGWK equals the language of restricted growth words of set partitions with K blocks. Now here we allow n to vary, and the length of the word of the restricted growth word is n, the n of which we are taking a set partition. And it's not difficult to show that W belongs to RGWK, this language, if and only if. Well, firstly, of course, K occurs in W because there is a kth block. And the second condition is that the first occurrence of I in W precedes the first occurrence of I plus 1. In W for all I equals 1 to K minus 1. You cannot put something in the I plus first box before you put something in the ith box, just because the least element of the ith box is less than the least element of the I plus first box. And here we are reading the elements from 1 to n. So this is a description of the language RGWK. And using this, you can write down a generating function, a regular expression for this language, for which every word has a unique matching. So RGWK is LU, where U is equal to the regular expression. So you have to start with 1 because the first occurrence of 1 occurs before the first occurrence of anything else. And then until you have a 2, you're only allowed to put 1s. So you'll have 1 star. Then you can have a 2. And once you have a 2, you're allowed to put 1s and 2s until you put a 3. And then you're allowed to put 1, 2, 3, and so on. And at the end, you have to have a K and then 1, 2K. And each word in RGWK will match this regular expression uniquely. And so what we get is L or maybe I'll just write the generating function of this language RGW of X is going to be, so we'll just take the it's going to be the product of these generating functions. So this is just X. 1 star is 1 over 1 minus X. This 2 is again X. 1 or 2 star is 1 minus 2X, and so on, and in the end we get X over 1 minus KX. Or more compactly, I can write this as product. I goes from 1 to K, X over 1 minus IX. And the number of words, number of set partitions of the set 1 to n with k blocks. This has a name. It's a classical thing that's much studied in combinatorics, is denoted S and K, and it's called the Stirling number of the second kind. So what we've shown is that summation n goes from 0 to infinity, S n k x to the n is product I goes from 1 to k x over 1 minus ix. And recall that the Bell number Bn equals number of set partitions of n. So it's just the cardinality of pi n. This is going to be some, so the generating function for, so this is going to be S n1 plus S n2. And of course, if you have a partition of n, it cannot have more than n parts. So it's Sn. But I can still, if I just take Snk to be 0 for k greater than n, then I can write this as summation k goes from 0 to infinity Snk. And so I get an ordinary generating function for Bell numbers. Summation Bn x to the n is summation k goes from 0 to infinity product I goes from 1 to k x over 1 minus ix. You should check that this expression here actually makes sense, in that this infinite sum converges.